In this section we're looking at other integration strategies. So we can kind of pull from all that we've learned, U-substitution, partial fractions, integration by parts, all those different things, and we can kind of combine them with some other strategies, and so that's what we're going to be looking at. Now, one of the things that we talk about in this section is using the tables of integration that are in your textbook. Now, if you haven't looked on your ebook, let's go ahead and pop that open real quick. Our ebook shows us some tables of integration. So let me see if I can find it. Okay, so for tables of integration, once you log into your ebook, you'll see over here on the side that we have the options of multimedia library, browser check, chapter contents, and I'm going to select chapter contents. And then if you scroll down toward the bottom, actually it's right here at the top under chapter contents, you'll see tables of integrals. So if you open up the tables of integrals, basically you have 3 pages, I believe, maybe there's 4 or 5, of different integrals. So basically we're using a U-substitution for all of these, but we have to get them into a form to be able to use this. Now once these tables of integrals open up, first of all I'd like you to know you don't have to have these memorized. You just have this as a resource to use on your homework and your handwritten homework if needed. However, any of the integrals that I'll give you on your handwritten homework or on the exams will not require tables of integrals. So what we do with the table of integrals is we find something that's close to fitting a form, and then we just follow through with the U and the A substitution and work forward from there. So that using the tables of integrals is basically U-substitution. Now I'm going to keep this available so we can go ahead and look at one of our first problems. Now let's make a list of strategies. So first of all, back in the day, long time ago, we learned U-substitution. And so if you can, this is one of the first things that you want to look at if a straightforward power rule doesn't work. So of course, I guess we could write power rule first. Now remember, the power rule is basically adding 1 and dividing by the sum. So we have a power rule, we have good old U-substitution. Now again, you should check for the easy things first. So check for the power rule first, U-substitution. We could look at something like expanding the numerator. So for instance, if we had an integral, let's say that was x to the 4th plus 2 quantity squared dx, we can't use a U-substitution on this because u would be x to the 4th plus 2, du would be 4x cubed, and I don't have that. So what I could do here instead is to actually multiply this out. Now if I multiply this out, I guess I'll just show what the result is. This would be x to the 8th plus 4x to the 4th plus 4 dx. And then I can use good old power rule on this. So that's what we mean by expanding the numerator. We can also separate the numerator. Now remember, you can only separate the numerator, never the denominator. So we don't want to just put separate, we want to have separate the numerator here. So if we talk about separating the numerator, we could have an example. Let's say we'll use an exponential on this one, but we don't have to. It could be used for any similar. Now I might try U-substitution here, but if u would be my denominator, obviously I have a lot more going on here for my du. So what I do is separate the numerator, and I'd rewrite each of these over the denominator, each term in the numerator over each term in the denominator. Now once I do that, I would simplify e to the 4x divided by e to the 3x. When you divide like bases, you subtract exponents. So this would be e to the x, 4x minus 3x is x, e to the 2x e to the 2x divided by e to the 3x, I'd subtract, so it would be plus e to the negative x, and then I'd pop this one up top, and that would be e to the negative 3x dx. And then I can use my U-substitution and integrate each of these, so I'd let u equal the exponent and kind of work from there individually. So that's an example of separating the numerator as one of our strategies. Another one is completing the square. Now complete the square will probably show up on your My Math Lab homework. I believe there's a completing the square on that one. I have it right here in front of me. So I'll sort through it real quick. And it does look like there's a completing this, well, it could be completing the square. It doesn't have to be completing the square, but I think that's probably the easiest one. So completing the square does show up in your My Math Lab homework, and it will also show up on your handwritten homework and on your exam, so make sure you know that strategy. We could also look at adding 0. So an example of adding 0 might be something like x squared over x squared plus 1 dx. Now there's other ways to work this problem perhaps, but one easy way would just be to go ahead and add 1 and subtract 1. Now the overall effect of this is adding 0. And of course if this was a plus 2 we could do add 2 subtract 2. And then what I do is I separate this out. So this would be x squared plus 1 over x squared plus 1. And then minus the integral of 1 over x squared plus 1. Now what we have here then, x squared plus 1 over x squared plus 1 is just 1 dx. And then over here, this is an inverse trig. In fact, it's an inverse tangent. So it's arctan. So that's an example of adding 0. Another strategy that we could do is a change of variable. Now we've looked at all of these before, I just am trying to summarize them all here. So for instance we could have something like x and then root x minus 1 dx. So our change of variable, I'd let u equal the radicand. I'd solve for x here, x is equal to u plus 1, du is dx. Now what the clue is here with why this has to be a change of variable, x minus 1 is u, so this would be x u to the 1/2, and then dx is du. And if you notice I have to change my variable here because I'm left over with an x. So in place of that x I would plug in u plus 1, u to the 1/2 du, and we work from there. Now this would be an example if we distribute. So that's another strategy that we've used before. We've looked at change of variable. We can look at simplifying, rewrite using trig identities. So a lot of times this would be checking for a U-substitution. It might not work, and so what we do is rewrite everything in terms of sine and cosine would be an example. And these trig identities could include any of the common ones that we've looked at, the Pythagorean identities, the double angle, the half angle. Another one here is to multiply by the conjugate, and this could be either in the numerator or denominator. That could be a strategy that helps us out. Now another one is to multiply by 1. One that always comes up with this one for me is if we have secant, 1 over secant. Is it secant or 1 over secant? Let me check real quick. It's secant. Because secant is not an antiderivative. So if I was trying to integrate this, what I do is I choose to multiply it by 1 basically. But I choose that value of 1 in a particular way. I multiply it by secant x plus tangent x. Now when I do this, secant x plus tangent x divided by secant x plus tangent x is just equal to 1. So that's the same as multiplying by 1. And then I have a dx in here. My u would be the denominator, and then my du would be the numerator after I distribute the secant. So these are all different strategies that we can use. Now there's other strategies that aren't listed here because we can't make a comprehensive list of all of them, but at least it gets us started. And of course our last one, and this is the most uninteresting one to me, is using tables of integration. So once again, on an exam, you're not expected to know the tables of integration, of course. I'll give you integrals that you can integrate by hand or that we have experience integrating or that we can use following one of these rules up here. Or if there's something that requires a table of integration, I'll provide it. Now in your homework we talked about the tables of integration, and they're also embedded in some of your homework problems. So let's look at an example where we're going to use a table of integration. And again, least favorite of all the problems that you'll be working are ones that pull from the tables of integration. So let's look at the integral of the sine, and always put parentheses around the arguments of your trig functions, sine of 17x sine 18x dx. Now I can't combine these because the arguments are different, so I can't call this sine squared. So we have to kind of be careful about this. Now if we look at our tables of integration, remember we just opened those, or I thought we did. Let's see if I can find them again. Here they are. So these are the ones that we just opened from our textbook online. If we scroll through here, we're looking for one that looks like two sines multiplied together but that have different arguments. So we're looking for trig functions, and I see it right here. Okay, so I think that's the one we're going to want. Whoops, that's sine cosine. Here's sine sine. So let's go ahead and take a screenshot of that and pop it into the lecture so we can kind of follow that format. So we're going to use this sine sine. Okay, and remember, I don't expect you to have these tables memorized or all of them in your notes, because I won't really just accept a table solution on a homework or an exam. So make sure that you're thinking about using these very sparingly, maybe to check your work, but they're not a justification for a solution. Okay, so if you notice, they don't put parentheses around the arguments of their trig function, but you'll want to. So what I have here is the sine of mx, sine of nx. And so what we have, we know m is equal to 17, and we know n is equal to 18. So this is our solution on this side. So my solution is going to be equal to the sine of the difference, and so we need to make sure we get this order correct. M minus n, so 17 minus 18x, over 2, I'm going to put brackets around this too because that's my argument, over 17 minus 18, minus sine of m plus n, 17 plus 18x, all over 2 times 17 plus 18. And then of course I have my plus c. Now this end part says that m and n cannot be the same, because if they were, we could just combine them and use a half angle formula. So let's simplify this. So this is the sine 17 minus 18 is a negative x. So again, parentheses around the arguments of your trig functions. Denominator is going to be 17 minus 18 is negative 1. Negative 1 times 2 is a negative 2, minus the sine 17 plus 18, 34, 35x, over 2 times 35 is 70 plus c. So this would be your solution. Now you typically will not see a solution with a negative argument. So a lot of times we like to rewrite those. So we could rewrite this using a sine identity. Now this is not sine as in sine, cosine, tangent. This is sine as in SIGN. And one of the sine identities say that the sine of a negative x is equal to negative sine of x. So we could rewrite using that. So the numerator would become negative sine of x over negative 2 minus sine 35x all over 70. Now remember, the 35 doesn't cancel into the 70 because 35 right here is part of the argument of the trig function. Okay, so we have to be careful of that. Negative divided by negative is a positive, so this rewrites to 1/2 sine of x minus 1/70th sine of 35x plus c. So when you're using the tables of integration, there's not too much to it other than you need to make sure if there's a u involved, you have a du. You might have to compensate there to make sure you have that. Or you need to make sure that when you're rewriting that you have the correct orders here. So that's an example of using tables of integration. Now a lot of times there's some pre-work that must be done in order for you to get something to fit a form in the tables of integration. Okay, so little work has to be done to make these match up. And those are the fun problems. So let's go ahead and look at a few of those. Some of these I'll just give you a start on, so we'll go ahead and write them out and give you a hint on where to go, and then you can kind of take it from there. Okay, so let's look at x over 7 minus x dx. So the first thing I notice here is if u is 7 minus x, du is negative dx, I'm left over with this x, and because I'm left over with this x, this tells me that this is a nice little change of variable problem. We might even be able to do this with an adding 0 as well, but I think change of variable will be our best bet. So change of variable, u would equal 7 minus x, du would be negative dx then. So if we substitute this in and solve for x, I get x is equal to 7 minus u. So subbing in, x is 7 minus u. 7 minus x is equal to u, and then my dx, I need to have a negative sign in front of it in order for this to work. So I'd multiply by a negative on the inside, compensate with a negative on the outside, and then I have my du. Okay, rewriting, I can separate the numerator now, 7 over u minus u over u du. So negative sign, 7 over u minus 1. This isn't 0, it cancels to give me a 1 here, du. So negative integral 7 over u du. The negative distributes, so plus integral 1 over, 1 du. So minus 7 natural log absolute value of u plus u. But u is equal to 7 minus x, and of course u is equal to 7 minus x plus c. Now we probably won't leave it like this because if we leave it like this, this argument might get mixed up with this 7 minus x over here, so we probably write everything out front and then the log. Now the rewrite on this one is a little strange. So if we write these out front, that would be a negative x plus 7 minus 7 natural log absolute value of 7 minus x plus c. Now remember, the c is a constant and so is the 7. So a constant plus 7 is just some other constant. So a lot of times you'll see all those constants combine, and this would just be minus x minus 7 natural log absolute value of 7 minus x plus your new constant of integration. So a lot of times these will simplify down to combine all of your constants of integration. Let's look at another example. In this one, we'll look at some hints here. X squared minus 4x in the square root in the denominator. Now when we're looking at this one, u would be x squared minus 4x, du would be a 2x minus 4. I don't have that. I can't do a change of variable because there's no other variable up here to switch with. This could look like a u squared minus a squared type of situation, trig sub. But before I can get it into a trig sub form, I need to complete the square. So I'm going to look at completing the square and then a trig sub. And the more of these problems that you work, the more familiar you'll see. When you look at a problem, you'll see, gee, this would be the correct strategy to use. So let's go ahead and focus on completing the square at first. Now when we complete the square, we don't have two sides here, so I need to complete the square on the same side of the expression. So the way this works is you take half of this linear term, which is negative 4. So I take half of negative 4 and I square it, and that's what goes here. So negative 4 divided by 2 is negative 2. Negative 2 quantity squared is 4. So I'm going to add 4, and if I add 4, I have to compensate by subtracting 4. Now what I want to do is I want to factor this x squared minus 4x plus 4, and of course the minus 4, I can just rewrite that as minus 2 squared. Now remember, the minus sign is not in parentheses. Now a good hint for factoring this, what was half of your linear term? Negative 4 divided by 2 is negative 2, and that will be the value that always goes here. Now if you had a 3 out in front of this x squared, I'd have to factor that 3 out first. So you have to be really careful about that. If your leading coefficient is not a 1, there's a little bit different process, a few more steps that you need to look at. So now that I've completed the square, I can rewrite my radicand, and then hopefully this will either fit a form or I can use a trig sub on it. So this is going to be square root x minus 2 quantity squared minus 2 squared dx. So completing the square is done. Now I'm going to use some trig sub here. So for my trig sub, it looks like to me that this fits a form of u squared minus a squared, and the substitution that's recommended is to let u equal a secant theta. Well, in this case, u is x minus 2, a is 2 secant theta. So you want to solve for x here. X is equal to 2 plus 2 secant theta. Dx, the derivative of a constant is 0, so the derivative of 2 is 0. Drag this other 2 along, the derivative of secant is secant tangent. And of course we have a bit of a d theta there. Okay, so this should be pretty simple to rewrite. So this x minus 2 right here is going to be 2 secant theta, and of course it's quantity squared. And this is minus 2 squared. Here we have our square root. Now dx is equal to 2 secant theta tangent theta d theta. So that's a substitution in for dx. So for dx I substitute directly in. Now my job here is to rewrite and simplify this. So the numerator, not much will happen here, at least at first. And then in the denominator, 2 secant theta would be the same as 4 secant squared theta minus 4. And then continuing to simplify, I can factor a 4. I'll be left with secant squared theta minus 1. And then I can break up that denominator into 2 parts. So I have root 4 root secant squared theta minus 1. You don't want to skip any steps here because there's quite a bit going on. Plus you want full credit for the problem. Okay, so the square root of 4 is 2. So these 2's cancel. And then secant squared minus 1, that's a Pythagorean identity, is equal to tangent squared. So the denominator is the square root of tangent squared. And of course, the square root of tangent squared is tangent, so the tangents cancel here. And I'm just left with the integral of secant theta. And I think this is one of the ones we talked about up above by looking at the multiplicative identity. So we've already talked about this one a bit up above. I have a hard time leaving these undone. So what we would do with this one is we would multiply top and bottom by secant theta plus tangent theta. So secant theta plus tangent theta. And this is multiplying by 1. It's just a strategy. It's a trick that works here. So distributing in my numerator, I get secant squared theta plus secant theta tangent theta. And then my denominator would just be secant theta plus tangent theta. So what we would do is use a U-substitution now. U is my denominator, secant theta plus tangent theta. Du, the derivative of secant is secant theta tangent theta. The derivative of tangent is secant squared theta d theta. Now if you notice, I have all of that up here. So this just rewrites into a nice little 1 over u to u, which integrates into natural log absolute value of u. But u in this case was secant theta plus tangent theta. Now this has been a long problem. It seems like we should be done by now, but you can see we're not quite done because my original problem was in terms of x, and so should my solution be. So let's remember what we used for our substitution here. We used x minus 2 equal 2 secant theta. So we need to convert back to x. X minus 2 equal 2 secant theta. So this tells me that secant of theta is equal to x minus 2 over 2. Cosine, secant is 1 over cosine. So secant would be hypotenuse over adjacent, because cosine is adjacent over hypotenuse. So we go ahead and draw out our triangle. It's kind of our key to getting converted back. Always mark your 90-degree angle. Always mark your theta. And so hypotenuse would be x minus 2. Your adjacent leg is 2. And then the opposite leg is going to be, using Pythagorean's theorem, x minus 2 quantity squared minus 2 squared. Now, keep in mind that that was my original substitution that I made up here after I completed the square. So this is my expression right here, and that always happens when I convert back. Now, that simplifies, but we'll look at that in a moment. So we have equals natural log absolute value of secant. Well, secant was x minus 2 over 2 plus tangent would be opposite over adjacent. And this is my solution, or a bit of my solution anyway. Natural log absolute value of x minus 2, there's a common denominator here. Now under this radical, I would get x squared minus 4x plus 4, and this is a minus 4, so I get x squared minus 4x. This was my original integrand that I was working with. So if we scroll back up, we'll see that this was my original integrand that I was working with right here. And that's really common to happen, and it's kind of almost something you should look out for as a kind of a checkpoint or a check figure. Now remember, the log of a quotient is the difference of the logs. And natural log of 2 is just another constant, so I can combine these. So this is just natural log absolute value of x minus 2 plus root x squared minus 4x plus c, my constant of integration. So that was a cool little problem. I had a lot going on. We were looking at completing the square first. Then I believe we looked at trig sub. And then after trig sub, we looked at multiplying by 1 is my strategy here. So here was my multiplying by 1. And then I had to convert back. So there's a lot going on with these types of problems. And in one problem, it's really easy to check to see if you have all of your integration skills there. Now when you're working, a lot of times it's hard to see what the appropriate technique is. So you have to try something. You have to start and try something. If it doesn't work, go back to the drawing board and see what you can do next. Now some of these I keep saying, oh, I'm just going to set it up and not solve it, but I have a really tough time leaving these without a solution. So let's go ahead and look at a few more. Maybe some of these I'll be able to leave. Now if you look at this one, it doesn't really look like it lends itself to much here. The first time I looked at this, I thought of this and I thought, oh, well, let's do a substitution and then maybe complete the square. So let's start with the substitution. So if I let u equal sine of x, du would be cosine of x dx, and I have that. So rewriting this, this would look like cosine of x dx is just going to be my du. So this would be 3u squared plus 5u. So this is my new integral. And then I looked at this and I thought, okay, well, maybe we could complete the square on this, but because I see this 3 in front, I think to myself, I don't want to complete the square on that, because my leading coefficient has to be a 1 in order to complete the square, or in order to follow our standard rules for completing the square. So I don't really want to go that route, but I do notice that this factors. So that would be the next thing I could look at. I could factor out a u. If I factor out a u, I'm left with 3u plus 5 du. So if this factors, I should be able to use partial fractions on this. So I should be able to use partial fraction decomposition. So this one I'm going to leave up to you to solve, but this is definitely a partial fraction decomposition type problem. Now, when I went through and solved this, I'll show you what I have for an answer, but I would check this on your own, go through the steps and verify it. I got 1/5 1/5 natural log, and then the sine of x, and again always put parentheses around the arguments of your trig functions, over 3 sine of x plus 5. Now when we're trying to look at this and think, okay, is the sine of x plus 5 part of the argument or not? So does it, the x is part of the argument, or is it the x plus 5? It's really important that you clarify that with the correct set of parentheses. So for this example, it's just the x that's part of the argument and then the plus 5, and then we have our constant of integration. So if you want to go through and check this by using your partial fractions, I would really encourage you to do that because you never know where it might show up again. So it'd be good to have worked through the problem at least once. Let's go ahead and look at another one. This one, it's just a matter of trying to figure out the correct value for u in our U-substitution and then making sure we have our du. So if we look at our argument here, I could use e to the t up here as my u, but then my du would be e to the t, and that's down here, so that doesn't really help. But maybe I can use this entire radicand for my U-substitution. So u would equal 7 plus 10 e to the t. Du is just going to be the derivative of 7 is 0. The derivative of 10 e to the t is 10 e to the t times the derivative of t, which is 1 dt. So rewriting, you can see I need a 10 e to the t, so I multiply by a 10 on the inside, compensate with a 1/10 on the outside, and it looks like to me all of this becomes my du, and in my denominator I have u to the 1/2. So this is 1/10 integral. I'm going to pop that up top so I can go ahead and use my good old power rule. So we'll go ahead and add 1. And I get u to the 1/2 divided by 1/2 is the same as multiplying by 2. So 2/10 is the same as 1/5 u to the 1/2. And u was 7 plus 10 e to the t all to the 1/2. I'm going to write this with a radical. So 7 plus 10 e to the t plus c, my constant of integration. So this is an example of a nice little U-substitution. But again, we have all these strategies. And I would suspect that on your handwritten homework and on your exam, problems that can combine many of the strategies will be the most useful type of problems to check to see if you know all of your different strategies of integration and how to incorporate them together. So to finish this up, I'm just going to go through a lot of different examples and get them set up and hopefully give you some solutions to them, or at least give you a start. So our first one is the integral of 3 over x squared plus 4 dx. This is just a nice little inverse trig form. So this fits the form of an u squared plus a squared. So this is going to be 1 over 2 inverse tangent of u over 2, because again this fits u squared plus a squared. So 3/2 inverse tangent x over 2 plus c. Now just by one quick change, we totally change how we're integrating this. So if I leave a 3x here now in the numerator instead of just the 3, this really changes. This becomes a u sub. So we'd let u equal x squared plus 4. Du would be a 2x dx. So I'd multiply by 2 on the inside, compensate with a 1/2 on the outside, and pull out that 3. And this would become 1 over u du. So this is 3/2 natural log absolute value of u. U is x squared plus 4 plus my constant of integration. So one quick change and it totally changes the entire strategy that we're using here. Let's go ahead and look at another one. Let's take this to a higher power, 3x squared over x squared plus 4. And it looks like to me on this one, if I could pull out that 3, This might be a little bit easier to work with. Now it looks like change of variable might be something here. If I let u equal x squared plus 4 though, du is 2x dx, and I have a lot left over, so change of variable is not going to work here. I think on this one I could do that adding 0. So I could go plus 4 and then minus 4 and then separate these into two integrals. So this would be 3 integral x squared plus 4 over x squared plus 4 dx minus 3 integral 4 over x squared plus 4 dx. And then you can see from here it's pretty straightforward. Here I have another inverse tangent. So here I have this other inverse tangent. And here this simplifies to 1. So the integral of 1 dx is what I'd have here. So I'd have 3x minus 12 times 1 over 2 inverse tangent of 2 over x. So I guess I could write that out. So after some work, this would, after some work, this would be equal to 3x minus 12, 1 over 2 inverse tangent of x over 2 plus c. And of course we could simplify this a bit, but that kind of gives you an idea of where we're going with that. And again, please do take the time to check these, because these are really good problems to have on your handwritten homework and on your exam, so it'd be nice if you will have seen them before. Here we have a secant x minus 1 in the denominator, and our trick to this one is to multiply by the conjugate. So the conjugate of secant x minus 1 is going to be multiplying the top and bottom by secant of x plus 1. So what I did is I essentially multiplied by 1. So as you work through this one, you're going to have to be really careful about how you rewrite things. You're going to simplify, separate numerators. But when you get all said and done with this one, this is going to be equal to minus cosecant x minus cotangent of x minus x plus c. So again, make sure you can run through the steps here. There's going to be a lot of simplifications, a lot of rewrites, separating numerators. I mean, this kind of has it all in the U-Substitution too. But this is how you get started with it. You multiply it by the conjugate. Let's look at another one. This one's going to be separating the numerator and U-Substitution. So if we started this one with a u equals 4 minus x squared, du would be a negative 2x dx, and I kind of have that right here. I could create that, but I have this 3 in the way. So I think before we do anything, let's separate this into two parts. So I'm missing a negative 2, so I multiply by a negative 2 on the inside, compensate with a negative 1/2 on the outside. And this negative 2x dx is going to be 1 du, and this will be u to the 1/2. Now over here, this one fits a form. And it will integrate into inverse sine of u over a. So I'll let you run through the details of this. When you get done with this problem, and we go through and we make that substitution and we integrate, flip this up top, it looks like to me we're going to have a negative root 4 minus x squared plus 3 inverse sine of x over 2 plus c. So again, the work is the important part here that you go through to make sure you can match these solutions. Let's look at another one. This one, let's have 1 plus e to the x in the denominator, and in the numerator let's just have a 1. So if we look at this one, it looks like to me that we could use this denominator, 1 plus e to the x as our u, but my du would be e to the x dx, and I don't have an extra one of those. So U-Substitution isn't going to work. So I think what we could try though is adding an e to the x in the numerator. But if we add an e to the x, we also have to subtract an e to the x. So it's that whole idea of adding 0. And then once we add 0, we separate the numerator strategically to make this a little bit easier to work with. And then we simplify. So this simplifies to a 1 dx, which is pretty straightforward to work with. And then over here I'm going to have a 1 over u du that I can work with as well. So again, make sure you work through this and verify that this is the correct solution, because again, it's a nice little problem that could show up again on a test or a handwritten homework. So it'd be nice if you'd work through it before then. Okay, let's look at one that's a little bit more complicated. It's not as straightforward. Let's look at a cotangent of x times the natural log of the sine of x. Now notice the sine of x is the argument of the log and x is the argument of the sine. So as we're looking through this, it looks like to me, gosh, if everything was in terms of sine and cosine, this might work a little easier. So cotangent is cosine of x over sine of x. And this is just natural log of the sine of x. And again, always put parentheses around the arguments of your trig functions and the arguments of your log. So starting here, I've got to start somewhere. So I'm going to let u equal sine of x. And then du would be cosine of x dx. And we kind of have that going on over here. So what this would look like was du over u, natural log of u. So that's not really helping me much. So that doesn't really work. Okay, so let's try something else. Let's let u equal natural log of the sine of x. Du, the derivative of the natural log of u, is 1 over u times the derivative of u. The derivative of the sine in this case is the cosine of x dx. So du would be cosine of x over sine of x dx, which I have because I rewrote this as cosine over sine, or you could just notice that it was cotangent. So what this looks like then, cosine of x over sine of x dx is my du, natural log of the sine of x is u, so this simplifies to u du. So this is a nice little integral. So when you get done with this, again, go through and verify the steps. You should get natural log of the sine of x all over 2, and then this numerator piece should be squared. So you have to be really careful about how you write that, where you get brackets and parentheses and everything else. So this is a long list of problems and strategies, and that's what you kind of need to get used to, is looking at a problem, trying to come up with how you work through it, or at least a strategy to start the problem. And a lot of times that's the hardest part, is getting started. And once you get down a path that works, then you just have to kind of keep going with it, because some of these can get pretty long. As usual, if you have questions, please let me know. I'm happy to answer any questions that you have. You can shoot me a text. You can set up online office hours. You can stop by my office if you're on campus. And also, you also have the option of the Pearson Connect to a Tutor. Good luck and have fun with these, and don't give up on them, because if you start incorrect, you just have to go back and start from scratch and see where you end up. Have fun.